Okay, greetings everyone. We are from group 7 are going to explain about condenser and how to design a condenser. So first of all, let us introduce our group member. Our group member is consists of Adidoro Prakoso, Imade Agu, Fania Novalin, M. Ihwan Rifki, Mi Rifki Ezra Farezi, and Narendra Yuda Aditama. So let's know about condensation. Condensation is a process where water vapor becomes a liquid. Why does condensation occur? There are two ways of condensation. The first one is the water vapor is cooled or the heat is absorbed by coolant, so it can reach the dew point and the phase change occur. Or the water vapor becomes so saturated, so it can hold water anymore. There is two types of condensation. The film-wise condensation, where the condensate tend to wet the surface and thereby form a liquid film. And then the second one is droplet or drop-wise condensation, where the condensed vapor form droplets on the surface, and the small droplets grow bigger and bigger due to continued condensation and slide down when it reaches certain size. The heat transfer of the drop-wise condensation is 10 times bigger than the film-wise. Let's move to the condenser. So the mechanism of condenser is the steam or the water vapor is enter the condenser from the upper side and go down contact with the pipe containing the coolant, and the heat is absorbed by the coolant inside the tube, and the water vapor is condensing become a condensate. There is two types of condenser. The first one is vertical condenser that consists of downflow condenser and upflow condenser. And then the second one is horizontal condenser. From the two types of condenser, the horizontal one are more often used because they can apply with smaller dimension than the vertical condenser.
Next one is how to design condenser. In designing condenser, we have to put attention in specific gravity. And the first one is we have to understand that in the condensation of pure saturated vapor, the vapors enter the condenser at the saturation temperature and leaves as liquid. And the pressure drop is less than specific gravity inlet and higher than specific gravity outlet. And the mass velocity inlet is the same as mass velocity outlet. Pressure drop, tubes, and shell are different. And for shell, we have to know that there is an equation, and for the tube, there is another equation like this. The difference is in the n+1, where S is specific gravity for vapor, and we have to consider or assume that no contraction, and both equations are on the safe side since the mass velocity of the vapor decrease.
Okay, the next is how to design a condenser, but because step by step how to design a condenser is pretty long, I will explain it in somewhere else. Wait a minute. Okay, this is the overall step by step how to design a condenser. The first step is we have to collect physical properties of the fluid that we have to place inside the condenser, and then we have to make a specification, dependency, and make an energy balance of our condenser, and then we have to assume value of our coefficient. We call it as U assume, and then after we assume it, we can calculate the delta TLM, correction factor, F, and etc. And then after that we have to determine the heat transfer area required, or A, with this equation, Q over U assume multiplied by delta TLM. And then we have to decide the type of our condenser, tube size, material layout, assign fluid to cell or to air in the tube side. And then we have to calculate the number of tube that we want to use, and then calculate cell diameter, and then estimate the tube side overall heat transfer coefficient. And then we move to the right hand side. We have to divide bubble spacing and estimate the cell side heat transfer coefficient, and then we have to calculate overall heat transfer coefficient by calculation, or we call it as U calculation. And then if our U calculation minus by U assume is around 0 until 30%, if yes, we have to estimate the tube and cell side pressure drop. But if no, we have to assume our U calculation as U assume and go back to the step 5. And then after we calculate the pressure drop, we have to make a specification whether our pressure drop is within the specification or not. If not, we have to go back to the step 6. But if yes, we can step to the step 14 if our design can be optimized or not. Wait a minute. And then if our design can be optimized, we have to go back to the step 6. But if not, our design is acceptable. Thank you.
Hello everyone. So this time I will tell you about the case, the calculation case in designing a condenser. So here's the case: a horizontal condenser required for the condensation of propanol using water as the cooling medium, and this is the pipe specification. So the first step is we need to determine the physical properties of each compound by using the help from the heat balance. So this is the propanol heat balance, and this is the water heat balance, and this is the physical properties of each compound by using the information from current first edition appendix. And then the next step is calculating the LMTD and the delta T. So by using the same information as above, we can find the LMTD. And the next step is we need to complete the data for the tube and the shell. It's the same one. Using the same books appendix, we can complete the data. So here is the tube data, and here is the shell data. And then after we completing the data, then we need to calculate the UT correction. Since we already used the trial value, so after calculating the UT correction, after we found the correction value, the corrected value, the next step is we need to evaluate the heat transfer in each side. So we need to evaluate the heat transfer from shell side and the tube side. After evaluating the heat transfer, so we need to evaluate our dirt factor from our design, from our specification, and then comparing it with the allowable dirt factor that provided in the problem statement. And besides the dirt factor, we also need to evaluate the pressure drop from our design, from our specification, and also we need to compare it with the allowable pressure drop that provided by the problem statement. So that's it, I think, in general. So this is the summary of our the calculation. So thank you.
And now we move on to the conclusion. In this chapter, we will conclude our study with the overall design of condenser. Now, the condenser design. The design of condenser, according to the case study, can be summarized into two common types of industrial designs, which are process flow diagram or PFD and isometric mechanical drawing. For the process flow diagram is designed with Microsoft Visio, whereas isometric mechanical drawing is designed with AutoCAD Plan 3D.
In this portfolio, the case studies we discuss are about a horizontal condenser is required for the condensation of 40,000 pounds per hour of pure and propanol coming from the top of our distillant column. From our design calculation, we get the dimension for condenser operating at 15 psig, at which pressure it boils at 244 Fahrenheit. And for the condensation of 228,000 pounds per hour of water at 70 Fahrenheit will be used as the cooling medium. A dirt factor of 0.003 is required with a lower pressure drop at 2 psi for the vapor and 10 psi for the water. The tubes are to be 3/4 inch outside diameter, 13 BWG on 1 inch triangular pitch, and 20 feet long. From data above, we can conclude that the current design is satisfied the condenser duty, even though the RD calculation is bigger than RD allowance with 2% error. Besides evaluating RD, the pressure drop are also still allowable. However, the calculated pressure drop in shell side is a little weird, where there is almost no pressure drop at all.
For the isometric mechanical design, we can divide the design into three types, which are the wireframe, a design of the detailed drawing of condenser frame, conceptual, a design of the 3D concept of condenser, and finally realistic, a design of which ultimately what will the design looks like when it's been made. Also, from the conceptual, we can see the left side of the drawing, which encompasses the detailed flow of condenser. So we have the tube inlet and tube outlet, shell inlet vapor, vapor fan, and finally the condensate flow. Finally, that's all from our group study regarding the chemical industry unit design of condenser. Thank you for your attention.